Welcome to all. Today I am going to see what is optical networks. Optical networks can be classified into two types. First generation of optical networks. In here, optical fibers is used for transmission in order to provide a very high capacity. Optical fiber networks provides high bandwidth than the copper cables and is less affected by the electromagnetic interference. Some examples of optical networks are SONET, also called as Synchronous Optical Network, and SDH, also known as Synchronous Digital Hierarchy Networks. Second generation optical networks. They have some extra functions like routing, switching, and intelligence in the optical layer. This second generation optical networks are better in terms of functions when compared to the first generation optical networks. Next, multiplexing techniques. So, why this is done means in order to increase the transmission capacity of a fiber. What are the types of multiplexing techniques that is employed means time division multiplexing and wavelength division multiplexing. So, this diagram shows the time division multiplexing, and here it shows the wavelength division multiplexing. See, these are the different channels. This is fed. So, slots. This bit will be occupying the first slot. This stream will be occupying the second slot. This lane will be occupying the nth slot in time axis. That is time division multiplexing. Seen here, different lambdas, that is different channels are fed as input. What does the output means? So the channel is wide enough to transmit simultaneously different wavelength in a parallel manner. This is time division. This is wavelength division multiplexer, as different lambda values are combined and transmitted. Next, second generation optical networks, because it provides a number of extra functions like routing, switching, and intelligence. So the structure of it will be a little bit complex when compared to the first generation optical networks. So here, this is the diagram showing the optical networks. It is having OEOs. This is the optical subnet. Then mm, the key network elements that enable optical networking are optical line terminals, optical add-drop multiplexers, and optical cross connects. Optical line terminal multiplexes multiple wavelengths on a single fiber and demultiplexes a set of wavelengths on a single fiber into separate fibers. These OLTs, as its name suggests, optical line or optical line terminals, are used at ends of an point-to-point WDM link. An optical add-drop multiplexes takes input as multiple wavelength or different channels and selectively drops some of these wavelengths locate locally while letting others to pass through. It also selectively adds wavelength to the composite outbound signal. An add-drop multiplexer has two line ports where the composite WDM signals are present, a number of local ports where individual wavelengths are dropped and added. Optical cross-connect essentially performs a similar function but at a larger size. These optical cross-connects have a large number of ports, ranging from tens to thousands, and are able to switch wavelength from one input port to another port. Both OADM, that is add-drop multiplexers, and cross-connects may incorporate wavelength conversion capability. So this is a diagram regarding it. So this is one of the wavelength division multiplexing routing network. We have routers, add-drop multiplexers, line terminals, cross connects, and so on. A number of wavelength is transmitted. Say, optical packet switching. This is the how signals are transmitted as packets, and we are using light. The packets are converted into light and is sent. So these are the packets. They are saved. The input packets, the form of light is saved in the input buffers, and header recognition is done. Then a switch. By suitable control, it is transmitted and it is saved in the buffers and sent. The mission of optical packet switching is to enable packet switching capabilities and traits that can't be contemplated using electronic packet switching. Networks must incorporate some form of time division multiplexing to combine multiple connections onto the transmission bit rate. At these rates, it may be easier to do the multiplexing in optical domain rather than in electronic domain. This form of optical time division multiplexing can be fixed or statistical. Those that perform statistical multiplexing are called packet switched networks, we say. Nodes take a packet coming in, reads its header, and switches it to the appropriate output port. The node may also impose a new header on the packet. It should also handle contention for the output ports. Suppose if two packets from different ports are coming in and need to go out on the same output port, one of the packets must be buffered or sent out on another port. Ideally, all functions inside the node must be performed in optical domain. Certain functions such as processing the header and controlling the switch get to the electronic domain. This is because of very limited processing capabilities in optical domain. The header itself can be sent at a lower bit rate than the data, so it can be processed electronically. So these are some of the basics regarding transmissions in optical networks: wavelength, frequencies, and channel spacing. Wavelength and frequency are related by the formula c is equal to f lambda. C is the speed of light in free space. It is a constant value given by 3 into 10 to the power of 8 meter per second. As we are going to use light to transmit the signal, we are using C. F is the frequency of the signal. Lambda is the wavelength of the signal. Channel spacing can be measured in units of wavelengths or frequencies. The relationship between the two can be obtained by differentiating this equation. So you'll be getting del F is equal to minus C by lambda naught square into del lambda. This is the relationship between this is the channel spacing and this is the difference of the wavelengths. Signals have equivalent representation in frequency domain, where energy of the signal is spread across a set of frequencies. This representation is called power spectrum or simply spectrum. The signal bandwidth is a measure of the width of the spectrum of the signal. So this one we can say it is a bandwidth. So the energy of the signal is spread in these range of frequencies. This is called spectrum. Also we can say wavelength standards. WDM system, that is wavelength division multiplexing systems, today use the 1.55 micrometer wavelength region. Y means for two reasons. First is the loss in optical fiber is lowest in this region, that is in 1.55 micrometer wavelength region the loss is less, and very good optical amplifiers are available in that region. The wavelength and frequencies used in wavelength division multiplexing systems have been standardized on a frequency grid by International Telecommunications Union, shortly known as ITU. It is an infinite grid centered at 193.1 terahertz. The ITU decided to standardize the grid in the frequency domain based on equal channel spacing. So 50 Hz or 50 GHz or 100 GHz. The yearly WDM system uses a C band or the conventional band, that is 1530 nanometer to 1565 nanometer, and L band or long wavelength band 1565 to 1625 nanometer. This band has become feasible with the development of optical amplifiers in this band. Optical power and loss. Suppose we assume we are transmitting a light signal with power Pt watts. In terms of dB units, it is written by this formula Pt into dB watts, that is equal to 10 log Pt in watts. It is convenient to measure power in milliwatts. So equivalency of the equation in milliwatts is Pt dBm. M denotes milliwatts. That is equal to 10 log Pt in milliwatts. A power of 1 milliwatt corresponds to 0 dBm or minus 30 dBW. A power of 10 milliwatts corresponds to 10 dBm or minus 20 dBwatts. As the light signal propagates through the fiber, it is attenuated or lost, that is, the power is decreased. At the end of the link, suppose the received power is PR. The link loss is represented with gamma and is given by gamma is equal to PR by PT. In decibel units, we have loss. Gamma is equal to 10 log gamma is equal to received power dBm minus transmitted power in dBm. dB is used to indicate the relative values of power, whereas dBm and dBW are used to indicate the absolute power value. For example, if Pt is equal to 1 milliwatt and received power is equal to 1 microwatt, implying that gamma is equal to 0.001, we have the transmitted power in dBm is equal to 0 dBm or minus 30 dB watts. Received power in dBm is equal to minus 30 dBm or minus 60 dB watts. Thank you, students.